Okay, thank you. I'm Frederick. As Ralph said, I teach philosophy here, so I'm sorry you're going to have to listen to a philosopher for the day. You know where the doors are, so this is the time to get out if you want. So you might wonder why this sort of topic of causality is hanging around in philosophy, and one of the reasons is that basically, while causality has become very popular again across the sciences and machine learning and statistics in the last 10 or 15 years, it was really unpopular in the first 50 years of the last 100. It was the bad word of the unscientific concept that you shouldn't be talking about. You don't want to mention causality in your work because that's not the scientific concept. That was the sort of idea at the beginning of the 20th century. But the philosophers kind of kept the work on causality alive through people like Hans Reichenbach, Wesley Salmon, and I ended up in the philosophy department at Carnegie Mellon where people were working on the technical side of causality. It strikes me as a little bit bizarre that other fields didn't take causality that seriously for a long time, because it seems a little bit strange that how you would make sense of your experiments, of moral responsibility, of all sorts of other features in your life if you don't at some point want to talk about causality. And so while you don't have to be quite as excited about causality as I perhaps am, I've drunk this Kool-Aid for far too long, I hope you will get something out of this. I was thinking for this day today is I'm going to start on the very easy conceptual side and really go through a causal analysis in the simplest case with the strongest assumptions that we can apply, just so that we can see how it works. And then I think if you get the hang of that, then you will see how one can easily make this more complicated or adjust it more to your field or to the sort of circumstance that you're in. I know this stuff. I've seen this stuff before. It's going to be super boring for me if you don't ask me a ton of questions. And you know, if you're not going to ask me a ton of questions, I'm going to put myself to sleep in the front here, and I'd much rather snooze on the beach than in Chen 130. So you know, get off your laptops, think a little bit, and get to the first question for me quickly, because I think if we get a discussion going here, it's going to be a lot more fun, not just for me, but you'll also get a lot more out of it. Moreover, I've never taught this sort of thing in this format before. I don't know what your backgrounds are. I don't know what your level is on this material. And you might find it super easy, or you might get lost on the second slide. And the only way that we can adjust and calibrate is that if you're going to talk to me. So I really don't want to do a frontal lecture for the whole day, but it really depends on you to stop me and to ask, and I'm going to force the questions if you don't come with them in just a bit. Okay? Does that sound good? So please just dive in and ask. So here's the thought. I'm going to do a little bit of just setting up this the stage so that we know what we're talking about and that we can make some sense and get some notation down, and then we can see how that goes. So very easily, let's think about what do we mean by cause and effect. Here's an attempt. Let x be a direct cause of y if there is an intervention on variable x that results in a change in y while you hold all the other variables fixed at some value. Okay? That's the thought. So that's the initial attempt to say, what do I mean by a direct cause? So let me just visualize this. So if I want to say x is a direct cause of y, then what I mean is that I intervene on x, I perform an experiment on x, yes? And while I perform that experiment, I hold all the other variables fixed at some value, not at any value, not for all values, but at some value. There exists some value combination at which I hold fixed the other variables, and I wiggle x, and if y responds, if y results in a change as well under those circumstances, then I will say that x is a direct cause of y. Now, you're going to say, well, hang on, what about some other variable between x and y? Well, the notion of direct cause here is with respect to the set of variables that I have under consideration. Right? So the notion of direct cause is with respect to the variables that I'm playing around with. Yeah? Great. Oh, first question.
I think I was going to look at the word sum here.
Yeah.
Some value.
Yeah.
Why qualify it that way?
Okay.
Is that just a way to kind of give yourself at least a chance of finding
So I might have a causal effect on you by saying something here in the room while all of you are quiet and you will hear me. But if all of you are shouting, you will not hear a thing. So do you want to say that I'm not a cause of having some influence on you? Well, you might want to say, while everyone else is quiet, I can actually have a causal effect on you, but otherwise not, right? And so, exactly. It's an existential quantification over the possible sets of values, right? And you want to say that we want to say that something is a cause of something else if there exists a setting such that there is an effect. And of course, you might say, you might demand for example, I demand for my vaccination, right, that it's not just in some very specific setting that has to be possible for me, right, but that maybe I want it under a broad set of circumstances. That's fine. That's then a stronger notion of causation, but this is perhaps if you go weaker than this, I'm not quite sure what you're getting. So, yeah. But great question. This is what we need. So please, more of this sort of question. This will help the discussion. So let's leave aside the other variables for a moment and just let's think about what we mean by the causal effect of x on y, knowing that we mean that we're holding the other variables fixed at some value. Then one way to think about it is in terms of this notion of potential outcomes. This is a kind of complicated concept, but I think you will find it intuitive once you see how it's supposed to work. So here's one unit, one person, say, who's getting treatment or who's not getting treatment. Yes? Just one person. And we give them treatment, so we set x to 1, and lo and behold, what we see is that they recovered. Y is equal to 1 as well. Okay? Now, these are our actual outcomes that we observe for this one person under treatment and that they then recovered. We can imagine that there are potential outcomes, namely what would have happened if we had not given that person treatment. In that case, they would not have recovered. Now, we didn't see this value, but we can imagine that there would have been a possible world where if we hadn't treated them, then they wouldn't have recovered, right? And now we have two potential outcomes. One where we say, what would have happened if x had been 1 if we had treated them, or what would have happened if x had not been 1. And what we want to say then about the unit causal effect is that the unit causal effect on the one person is just the difference between the potential outcomes. Now you're going to say, how do I know that for one person? You don't know that, but that's what we mean. That when we say there is a causal effect that the aspirin helped get rid of my headache, what I'm saying is that there was a potential outcome that if I hadn't taken the aspirin, I would have still had the headache. Yes? So these potential outcomes are conceptual variables to help us think through. You can think of it as possible worlds if you want, not in the physics sense, but in the philosophical sense. And of course, we have to make sure that what happens in the actual world is consistent with the potential outcomes, right? So that if indeed we set the treatment to 1, and the potential outcome says then if you set for this person, you set the treatment to 1, then their outcome will be that they recover, then we would also want to make sure that the actual world is consistent with the potential outcomes. It would be good to have a question here because this is where I generally lose half the people. Yeah.
So treatment to recovery isn't a one-to-one, so do you not have to account for the potential outcomes of like, we gave this treatment and this person didn't get better, my headache didn't go away?
Okay. You're a different person then, right? So you're not this person. In this case, it seems to, in this case, it would have helped, right? But your potential outcomes could have been different. And so for a different unit, your potential outcomes would have been different. And so what's interesting then, right, if we want to study causality, is to say that, okay, what are the potential outcomes for everyone? Or what's the average treatment effect rather than the unit treatment effect? So you're absolutely right. I could have a person where it's both 1s here, or as you described, it's both 0s here. No matter whether I give them treatment or not, they're just hopeless. They're never going to recover. Right? Does that make sense?
So why then do you limit the potential outcomes for this one unit to these two numbers? Could have been the other way around, right? It could have been that the patient survived with x equals 0 and died.
Good. You're a person then where it hurts, where the treatment hurts. It could have been 0, 1, it could have been 1, 1, it could have been 1, 0, it could have been any of those combinations. right? So the interesting question is, what is it for each person? Maybe we can't infer that, but maybe we can infer the average effect of whether there are more people for which it helped than for which it hurt. I'm not saying that. I'm saying this is an example unit. The unit that you suggested would have 0, 0 here. The unit that you're suggesting has 1, 0 here, right, because the treatment is hurting. And then, of course, there's a fourth unit where it could have been, which am I missing, that they're always recovering, no matter whether you treat them or not, right? Yes? Exactly. Yeah.
So you're basically saying for each unit, they would have only a subset of the potential outcomes. For example, for subject A, if x equal to 0, y can only be 0 or 1. You can't have potential outcomes of y being 0 and 1.
Well, so yes, that's right. The actual outcome, you're only ever going to get one of your potential outcomes, right? What actually happens to you. But we can imagine, like, yes, what would have happened to you, and then if you had been treated, then maybe you would have recovered or not recovered. You will have one of those, right? And if you hadn't been treated, then maybe you would have recovered or not recovered, right? Yeah, so I think I want to agree with what you said, so yeah. Good? Okay, yeah, sorry.
For the direct cause here, you mean determined or with some kind of confidence interval?
So confidence intervals are about inference, right? Is that when I am trying to estimate something. Here at the moment, I'm describing the world as it is if I knew everything, right? Even if I knew possible worlds, right? Of that might have been different. So in the end, of course, we might not be able to estimate this sort of thing precisely and have to put confidence intervals somewhere. But what you might be asking as well is that could there be probabilities here, right? That's a little bit more complicated because it's not quite we'd have to be very clear then about what we mean by those probabilities, because those will be probabilities in different possible worlds, right? So generally, the potential outcome framework, which this is building on, does not use probabilities. It has deterministic values of either you have 0 or 1, right? Or if, of course, there could be more states than 0 or 1. Maybe it's a linear model, then it could be all sorts of different values of states, right? But it's a definite state, generally, yeah. There are, in the literature, some attempts also to integrate a probabilistic notion here. Okay, great questions. It gives me the sense that we're on the same page, so that's good. So I've basically said this already, is that, look, what we get to see in our actual experiment, right, is only the actual outcome. That is, we see, because we happen to have treated this unit, we see that for this potential outcome here, where we treated them and the outcome was 1, that's what we get to see. Yes? What we don't know is for that person who we treated and who had a good, who was helped, we don't know what would have happened to that person if they hadn't been treated. That's why one way to think about causal inference is about a massive missing data problem. We're missing half our data, basically. Yes? Because we don't know what would have happened to each unit if they hadn't been treated, or if they're in the control group, if they had been treated. Oh, okay. Please ask. I really don't want to lose you. I think this will be much better for everyone if there are lots of questions. So, okay. So now you might say, okay, can I experiment on the same unit again? In some cases, we think that's okay. We can do within subject designs. Sometimes we think that's okay, right? And then you might say, okay, I'm going to treat them again. Or sorry, I treated them the first time. The second time around, I'm not going to treat them, right? And then you might even get access for the single unit to both the potential outcome for when they were treated and the potential outcome when they were not treated. In some circumstances, we think that's okay. We can do the experiment on the same subject again, and we don't think there's any sort of influence between the two cases, right? In other circumstances, we say that, well, if I gave the exam to you once, right, and you performed fantastically on it, and next time I don't give you the exam, sorry, if I give you the training once and then you perform fantastically on the exam later, then we might say that, well, if I next time don't give you exam, then, well, if I don't give you the training, then will you perform as well on the exam? There seems to be an influence between the two tests that we're doing, right? So whether or not you can experiment on the same unit again to see the other potential outcome is a question that you have to assess and determine in your particular domain, right? So here we're looking at the same unit, not at two different units. Yes? No? Maybe?
Maybe to make that concrete a little bit, I'm
Yeah.
familiar with. A lot of these economic single choice decisions that maybe come from like Kahneman Tversky type world where I ask you a bat and a ball cost $1.10.
Yeah.
Whatever. And so almost like as soon as I ask you the first question, you're tuned to the riddle.
Yeah.
That is going to
Yeah. So then you would say no to this. You can't do this sort of thing, and then the causal inference problem, as you would expect, is going to be much harder, right? Because you don't know how I would have responded under a different treatment.
But
Right?
this might be, I've always been bothered by these experiments because it's always these one-shot questions. One person gets asked one question, and that's the end of the
Yes,
collection.
yes.
This gives a reason for it.
Yes, but also realize that you're demanding something very strong. You want to know for every single unit their specific causal effect. So for every one of you, I want to know what would have happened if you hadn't had this lecture. Well, I don't know what would have happened, right? For some of you, it might not have hurt not to have this lecture. So, but maybe we can still say something about the average causal effect across the group, even though we can't do it for the single person, right? Yeah, exactly. Great. Okay. So in this case, we already discussed this. Look, it looks like the treatment in this case helped because the potential outcomes were 0 and 1, depending on whether I did or did not get treatment, right? But what changed in that slide? Sorry. So we can have then a whole lot of different units instead. So if we can't do the same experiment on the same unit again, then maybe we have to look across a whole pile of different subjects, right? And here you see that there are the different potential outcomes that both of you already suggested here, that maybe there are some people who the treatment didn't do anything for, right? Maybe there are some people where it hurt, right? And so, unsurprisingly, we describe these people as like, okay, these two people are people where the treatment helped. This person is, they're never recover person. You can't do anything with them. The treatment doesn't do anything. This person, you didn't need to give them the treatment at all. They always recover, right? And this person, it hurt, right? And so we don't know, of course, for any single unit what their potential outcomes is. But if we could look under the hood, then this gives you the full story. Yes, no, maybe I know this potential outcomes framework. I take it is not totally familiar to you, right? So it's a different way of thinking. What I'm hoping is that it's actually quite clear if you get your head wrapped around it. Yeah.
Something is clashing
Yeah.
in my brain. I'm going to ask a very poorly.
Yes, go for it.
It seems like this, we can determine that the aspirin cures the headache if we had a whole list of people where it said help. Okay, this looks pretty consistent that this medication is doing something about this, which seems almost like a positive demonstration of causality, which seems to be kind of the opposite of typical hypothesis testing, which is, can I falsify this hypothesis? Is there I think the two are,
Yeah. So
it sense that the two are amenable.
yes, yeah. So first, of course, notice you don't know whether any person is a helped person or a not recover person, or sorry, they're not a never recover person, because you do know that, right? Because they had a positive outcome, but you don't know if they're a helped person or an always recovered person, right? So, but you're right. Of course, what we would like to say about aspirin is to say that we would ideally like to establish that everyone is in the helped group, right? But maybe we want to say it's fine not to have everyone in the helped group as long as the majority is in the helped group, or as long as not too many are in the hurt group, or something like that, right?
Okay, I've actually
Yeah.
my question is becoming clearer to me now. So if we had a situation where we had this kind of muddly thing, like we do here, is this an indication that either the aspirin is not causally related to curing headaches, because we can give people an aspirin
No. So wait. So it's very clear for these two people, the aspirin helped.
Imagining
Yeah.
where the help people are not there.
Well, okay. Then just wait a couple of slides. I think it will resolve itself.
Since we're only applying like one treatment per unit, shouldn't there be question marks?
No. So you're right. So what I'm saying is that this is if you knew everything, if you could look under the hood. You only get to see this. You don't know as a result. So here, then what you get to see, right, is this outcome, right, which is a different one for each of these people, which means that you have no idea whether these people are helped or hurt or whatever, right? And so so I think that's what you're getting at, right? And so now what I might want to say is that, well, I'm going to be happy with my aspirin treatment if my average treatment effect across the entire population is positive. What does that mean? It means that if I could, I don't see it, but so what I would like to have is that if I went across the entire population and I overall saw that on average aspirin helps, then I'm going to say it has a positive average treatment effect or negative average treatment effect if it hurts. Yes. Now again, I've not told you how to actually compute this. I'm just telling you what does it mean, that quantity. This quantity means for each person I'm going to take the difference between the potential outcomes. Right? Now I don't see those. I can't estimate those yet. I don't know because I've got question marks all over here. But if you think about what this actually means, it's the probability of the people helped minus the probability of the people hurt. Can someone explain why that would be the case? Why do the never recover and the always recover people not feature in the average treatment effect? That the difference is zero, right? For the always recover, the potential outcome here is 1, and the potential outcome there is 1, so the expectation is also 1. For the never recover, it's 0 in both cases, so it doesn't matter. So you really are looking only at the people where it helped versus where it hurt. Now, how do we get that number if we only get to see this, right? That's the question. Okay. Now we're going to do a tiny little bit of, so what does it mean? This average treatment effect is the percent of improvement that you would see if everyone was treated versus no one was treated. Okay, that's what the average treatment effect is. So how can I estimate that? Okay, what's the first line? I'm just taking expectations through. Nothing exciting happening here, right? Now, if I assign my treatment randomly, if I'm in a randomized controlled trial where I roll a die in order to assign someone to treatment or to control, then these quantities, what I get from the potential outcomes, are independent of my treatment. So which potential outcome I see is independent. So I can just add in a conditioning claim. This is equal. This is because of the independence that I get when I randomize. And then by consistency of the potential outcomes, I can see that I just have to subtract the expectation of y given x equals 1 minus the expectation of y equals x, y given x equals 0. And these are quantities, both of these are quantities that I can estimate from here. Because the last line just specifies how often in my control group do I see y equals 1 or 0, and how often do I see 1 or 0 in my treatment group. Now notice what we've just done. For something where we didn't see the potential outcomes we didn't see one of the potential outcomes for one of the individuals, we've just gone through and said that, okay, if we assign treatment randomly, we can actually estimate the average treatment effect, not for the individual, but across the population, by just looking at the outcome of the experiment. I've lost everyone again, so we're going to need some questions. So think about where you got lost.
It's a little bit difficult for me to understand that the probability we're talking about here is in the population level. Why don't we care about the probability in the individual level?
Yes. So remember, the thought is that if I take my aspirin, there's going to be one outcome: I recover or I don't recover, right? So this is what I can actually measure in my data, right? I recover or I don't recover as a result of taking the aspirin. There's no probability to that. Something's going to happen, right?
It could be someone cough every day, from coughing every day to coughing every day.
Yes, but that I don't have in my data, right? So I don't get, I'm going to have some, so you're thinking okay, maybe this goes back to a question that was there earlier. The potential outcome is either you recover or you don't, right? So you're now saying that, well, maybe there's a certain probability to recovering or something like that, right? Even when I'm treated. So if I give a patient aspirin, right, then what do I measure as outcome? Am I measuring a determinate quantity, like they get better or they don't get better, or am I measuring a probability? And I think what you have in mind is you want to say, well, maybe they're only recovering with a certain probability. But then what is that a probability over? You don't see that probability. You have something else in mind. In your data, you're just going to have they did or did not recover. And that's what this is measuring, right? That's what this is building on. Maybe come back to it again. How about some other questions? Because I feel I've lost a lot of people here, and there's no need to lose everyone because I have time.
I'm going to ask
Yeah.
a question, and I hope that the answer will be elucidating.
Okay. Oh dear.
The middle equal sign there.
Yeah.
You said if X is assigned randomly, then I can just add this arbitrary condition.
Yeah.
You could have picked the other conditions. You could have said on the left-hand term, E, Y, X equals 1, given X equals 0.
Yes.
It would have been completely reasonable thing.
Yes, but then I couldn't have gone here because I would have violated consistency. Right? Because I need these to align in order to go for, if you had put 0 here, I would have had X equals 1 here. And X given, what is my potential outcome if someone had been treated, given that I didn't treat them? I don't know what that is. I can't convert that into something that I observe.
But it nevertheless should be the same number.
No. This is that would be no. It is a defined number, but I don't get to see it. What my goal is to convert. I want to end up with quantities that I actually have in my data. These quantities I have in my data. If I have the potential outcome of y what's the potential outcome of y if I set x equal to 1, given that I've set x equal to 0, that's you're saying that what would my outcome have been if I had been treated, given that I wasn't treated? Well, I don't know that.
But aren't you telling me by that statement on the bottom left that that is in fact the same number?
No, no, so careful. So it's the same as this one, right?
Exactly. All those 3 numbers that you wrote down and the 4th one that I'm proposing should be the same by that independence statement. No?
No.
Okay, then I'm
So-
officially indeed confused.
No, but do you agree I couldn't go from here to here?
Yes, but now I don't understand how you can go from the first line to the second line if you can't go from the first line to my 4th line.
To your fourth. So I can add in. So you want to have x equals 0 there.
Because I think what you're saying there by the middle equal sign,
Yeah.
that because y and x are independent, I can put in.
No, not y and careful. It's not y and x are independent. It's not that these two are independent. It's not that these two are independent. It's that you have that x is independent. So x is independent of these guys. Right? It's x is independent of the potential outcomes. It's not that x and y are independent.
Right, but regardless, you were allowed to write given x equals 1 there
Yeah.
because of this independent assignment.
Yeah.
So I think that I can also write down x equals 0.
Yes, you can.
And then
But
I get a number that I can't interpret, but that nevertheless has to have the same numerical value.
Yes, it has the same as that, but it doesn't go to here. You can't. So what you said is right. It's the same as this, but you don't get to anything observational.
Right, so it's the same but it's useless.
Yeah. Well, you don't know it. You don't have access to it, whereas you do have access to this one. This one I have in my. This is just observational data. There's no potential outcome here. Maybe we'll come back to it. Okay, let me try a different way of explaining it. So this is suggesting that, look, what I can get my average treatment effect by just looking at what happens to y when I intervene on x. I can estimate that. You shouldn't be surprised by that because that's what you do experiments for. We randomize x because it specifies what happens under intervention. What happens when I intervene on x and I look at y, that's what the randomization specifies. And that's what we mean by a causal effect, because it controls for the sort of confounding that we might see. It breaks the causal influences from a confounder. We can just, when we randomize x, we break the influences from other confounders and see what effect x has on y. That's why we do experiments. We want to make the intervened variable, the potential cause, independent of other confounders. And so it's not surprising that we think that we can identify the average treatment effect from a randomized experiment. That's what I think you've all thought all along. That's why you do randomized experiments.
So it's still considered, I think it is, a causal relationship if, let's say, unbeknownst to us, x is causal on this, let's say, w, the top in the triangle. Let's say every time I take an aspirin, my aspirin is also causing me to do, the aspirin causes me to do some other behavior, and that behavior gets rid of my headache. So if there's this kind of chain.
Yes. So you could imagine there's something on the chain right here in the middle. So what I said at the beginning is the direct effect is relative to the set of variables that you're considering, right? And if you're not holding fixed this variable in the middle, then of course you have an indirect effect through. So we can talk about an indirect cause or a total cause, right, along all the pathways that are between x and y, right? And that then depends on what you're letting go or what you're not letting go of. The key is that we think that we can estimate the causal effect of x on y given the randomization, and then it's like whether it's direct or indirect depends on what else you're holding fixed or measuring. Yeah. Okay, I'm quite concerned that I've lost too many of you, but we'll see whether we can recover that. So here, I introduced this notion of probability of y given do x, which if you've done any probability theory should be an unfamiliar term to you because the do operator doesn't appear in Kolmogorov axioms or whatever you like in probability theory. So what does it mean? Why do we have to why can't we just talk about the conditional probability of y given x? Why do we need the probability of y given do x? Well, it's because we needed the random assignment here over the unit of treatment over the units in order to make this causal effect identifiable. And that's why we have to also talk about an intervention distribution that represents that sort of random assignment. So here is where the difference between the probability of y given do x and the probability of y given x then becomes clear. If you intervene and you have a causal effect of x on y and you have a confounder, some unmeasured common cause, then the intervention will break the influence of the confounder. Right? That's the thought. That's why we randomize. And then the probability of y given do x will not be the same as the observational probability of y given x. Why? Why will it not be the same? I should be able to recover most of you here. Why is it the case that if I have this sort of causal setup, I have a causal effect and I have a confounder between x and y, I now intervene on x right there. Why is it the case that the causal effect of y on x is not just given by y, the probability of y given x?
Sorry, but the do operator here is enumerating over possible
Yeah, yes, you're setting, it's as if you set to treatment 1 or set to treatment 0. Okay, I've lost too many, so we really have to do some work here. Let's take the last one first. We have just confounding, right? There's a common cause of x and y. Are x and y going to be dependent or not?
Yes,
Yes, why? Say a little bit more.
because they're both caused by dots.
Yeah, can someone else give me an example of this sort of setup? We're going to have to do some work. I lost you 2 slides ago, so we're going to have to do some recovery. So let's try the recovery. Can someone give me an example of this setup to illustrate why x and y would be dependent? Oh, come on, don't leave me high and dry.
X and Y are 2 thermometers being caused by the temperature, so the temperature changes both ways.
Exactly. Okay, so that seems fairly straightforward. Now, if I intervene on one of the thermometers, right, and I just move the, like I heat that thermometer up, what happens to the other thermometer? Nothing at all, right? The other thermometer stays the same. So probability of y given do x, the other probability of whatever value the other thermometer has given that I'm heating one thermometer, right, is just going to be whatever the probability of the other thermometer was anyway, right? I'm breaking, by intervening on the one thermometer, I'm breaking the influence that the general temperature in the room had on both thermometers. Give me some feeling that I'm saying something that makes some sense, because I feel now that we're back to, we should all be on the same page again. Yes? Okay. So is that the same as probability of y given x? No. Why? Can someone explain this one?
Because the effects of x, the thing that's changing x change is irrelevant to y.
Yeah, that's right. So while observationally, right, if I hadn't heated my thermometer, I could look at the one thermometer, I could predict what that thermometer over there was going to say, right? It was going to say more or less the same thing, right? But if I'm heating one of the thermometers, I can't do that anymore. So the conditional probability under intervention is different from the conditional probability under observation. Yes? I'd like to have everyone back on track again at this point, right? Okay, so let's do the same game here, right? Why is this the same? Why is in this case the probability under intervention of y given do x, I intervene on x, the same as the observational one? Oh. Now you're not cooperating because I know that you all could answer this one.
So would this be an equivalent?
You've said too much today already, so I'm not going to. I want more from you, but not on the easy question. I need someone else for the easy question here, please. We're going to be bored out of our minds, and you're going to retreat to your laptops if it's going to go on like this, right? So let's.
Just declared it's an easy question that people aren't sure. That's not fair.
Okay, I'll do this one. You can think about the hard question then. Okay, probability of do x, y, is it the same? Well, here, one thermometer, well, let's not do a thermometer, right? I'm having an influence, the aspirin is treating my headache, yes? Well, no, that's not a good example because that's like an intervention already. So let's think about what's a good causal effect. So you have. No, the barometer is no. That's that case there, right? The pressure and barometer cases. So I have I turn the key in my car, my motor starts. Yes. Now, if I intervene to turn the key in my car, I see the motor is starting. If the key turns in my car, the motor will start. If I observe it happening, or if I intervene to make it happen, it doesn't make a difference. The observational probability distribution is the same as the interventional. But of course, it's different from just the car motor just starting up just like that, right? So just if there's well, the car motor is not a good example either. So let me see.
Well, how about this one? Clouds above the sky determine the temperature on our thermometer.
Good.
So x is the clouds in the sky, y is the thermometer.
Right.
Now we get a big leaf blower and we blow the clouds away.
Right. So in both cases, we can predict what the temperature is. Yes, under intervention, it's the same as under observation. Yes, maybe, no? Oh, you're not inducing confidence here.
It's funny that this is a difficult scenario to develop a coherent
I have one.
example of.
Like drinking coffee makes me more awake.
Okay.
But more awake can be caused by some other factors. Like UI would be very different.
Yes, yes. What I'm worried about that example is also that the drinking coffee is like an intervention already, right? So you can intervene. It's like the car key example, right? But so you're right.
Caffeine makes me more awake. It doesn't matter whether I drink it or whether you inject it into my bloodstream.
Okay, fair enough. So I think I'm hoping that this example. Why?
Is this potentially an example? Like, is placebo an example of this scenario?
The trick, the difficulty we're having with this example is that we immediately think of interventional cases, right? I switch the light switch, the light comes on. But of course, then making the distinction between what are we observing, right, versus when am I intervening, it's the same thing, right? That's what's happening. So we need something where, so the classic example, right, is
Or the heat and the next duration, the falling time.
so dropping a ball. But again, I'm letting go of the ball, right? It's like an intervention. So we want something that's more observational. Okay, never mind. I'll think about it in the break for a really good example. So that.
This might not be a good one, but what if imagine you have plants in your garden and you observe it's raining and it's good for the plants. So then you can also intervene and water your plants.
Okay, good.
You can both intervene and observe.
Okay, good. So in that case, I've got watering. So I can observe the rain on the plants. They grow more, right? If I now intervene to water them, right, they also grow more, right? The probability of intervention of if I add water on the growing is the same as if I had just observed more rain on the plants. Right? Yeah, I think that's good. If we lived in a rainy place. Okay, let's not make it too complex. Let me move on. I'm a little bit embarrassed that I've got such a yeah. Yeah. Okay. So what about this one? Back to the actually complicated one where it's a mixture of the previous two, right? In this case, I'm saying that the interventional probability is not equal to the observational one, nor is it the case that y is independent of x. And that's the tricky one. Does anyone have an idea of why that's the case? Never mind a concrete example. This is a complicated one to find a concrete example for. Let's just see whether we can explain it, what's going on mathematically here, why that's the case.
So the assumption then is that X has some independent agency that is in fact not directly and purely driven by dot.
No, the thought is that here I'm intervening on X, right? When I'm intervening on X here, I'm breaking the confounding. So there are two reasons why X correlates with Y, or why X and Y are dependent. One is because X causes Y, and the other is because there is a common cause of both of them, right? Now, when I just observe the probability of Y given X, I can use both the confounding aspect and the direct causal effect to predict what will happen to Y, right? That's the observational case. When I intervene, I'm breaking the dependence that is induced due to the confounder, due to the common cause. I only see the dependence due to the causal effect. So that's why probability of probability of Y given do X is different from probability of Y given X. Yes? But of course, even if I intervene, it's not the same as if Y were just independent of X. X still has an influence even under intervention on Y. So it's not the case like here where if I intervene, I break the connection between X and Y completely. There is still an influence, but it does mean that the interventional probability is different from the observational one, which is different from just the probability of Y. Yeah.
So what if we take the thermometer example again? So the confounding factor that influences both would be the temperature.
Yeah.
X would be direct measure of the temperature, and Y is another thermometer where we programmed it to be the current temperature plus whatever X is showing.
Yes.
So Y is being both influenced by X
Yeah.
as well as the real.
That would work. That would work. And then, so in that case, what happens, right? If I do probability of y given do x, right, then my first thermometer is not being influenced anymore by the temperature, the ambient temperature, but I can set it to 100 degrees or 200 degrees or whatever I want, and then as a consequence, this will change, right? So I will have that, but that will be different from the observational case where I just see the first thermometer at a particular value and it influences the other thermometer together with that. Yeah? Maybe? Oh man,
For me anyway, this is clear without examples. What you just described, but it is what we need to do experimentally.
yeah, yeah. I'm really a bit bummed that I ran myself into such a hole on this slide because this I had hoped would make it easier rather than harder. But okay, so what's the point? So just to hit the point home here, and what I want to get out of this is that if we just looked at the standard probabilities that we get out of the standard Kolmogorov axiomatization of probability, we wouldn't have enough tools to distinguish properly between interventional cases and observational cases. We wouldn't be able to pull these three cases apart properly. And so we need this operator, the do operator, which indicates that we're influencing or intervening on a particular variable to distinguish these sorts of cases. Okay? Yeah. So let's make this a tad more mathematical and see where, but we do it in terms of the very, very simplest model, namely a linear Gaussian structural equation model. So what do I mean by this? Suppose that what's going on out there in the world is described in terms of three variables, and the three variables are related just by linear equations, and in each case the variable is influenced as a linear function of its parents plus some independent Gaussian noise term. Okay? That's the thought. So what does that mean? I'm saying here each of the noise terms is a normal with mean 0 and variance 1. But what does that mean? I haven't specified whether there's dependence between this, so I just want to be quite explicit. If we looked at the covariance of the error terms, then we'd have a diagonal matrix with 1s along the diagonal and 0s indicating that there's that each of the errors is independent of one another, right? So that's the thought. We'd have just a diagonal covariance matrix. What does this sort of system look like when we intervene on x? Well, if we intervene on x, we take full control of x. That means this equation here gets replaced in the sense that x is no longer dependent on z, that x is now a function of just what we put in as the intervention distribution, right? So I'm wiggling x now. X is no longer controlled by z. That's my intervention distribution. But everything else about the model stays the same, right? So I'm replacing just the structural equations with an intervention on x, breaking the connection from z to x. Should seem like what you would expect would happen if you did a randomized control trial. Okay, so with those pieces here, we can now think about a specific case of a counterfactual. So I want to go through of how one might analyze a specific causal setting. Suppose we have one patient, and suppose for the sake of argument, we know exactly how the system works. So we have the full structural equations that represent the causal effect of treatment on this person, okay? The person is getting treatment, and we're asking whether or not they're going to go blind. In this case, it's not a linear structural equation, but blind is going to be that function there with an error term coming into the blindness. That's a Bernoulli distribution with 0.01 for coming up heads. Was that a question?
Where does this equation come from?
In this case, we've got God's view. We know everything. I want to just play through what would happen in this case. Yeah. So We've somehow learned it. Let's not worry about how we learned it in this case. Okay. It's contrived to make a point. Okay. So I can say what happened to this particular patient. This patient was treated, okay? And what we observed when this patient was treated is that they went blind. Okay? So this is bad news, obviously, for the patient, right? But note what that implies. If you look at the equations and you work through them, it implies that in that case, the error term on B must have been 1. Does everyone see where that's coming from? In order to have the patient go blind, even though you treated them, the error term has to have been 1. Okay? Now we can ask, as the patient might, right, what would have happened if treatment had been 0? Note, this is a counterfactual. This is a counter to fact question. The patient was treated and they went blind. We can ask what would have happened if they hadn't been treated, right? Well, how do we assess that sort of question? I think what we would want to do is we would want to take the question here with the knowledge that the error term must have been 1 and ask, like, if we keep the error term at 1 but substitute t equals 0 in, what would have happened, right? Because the error term represents the background that the patient was subject to in that moment. If they hadn't been treated in that moment, you notice that then, under that circumstance, the patient would not have gone blind. Yes? Does everyone see it, or is working through the equation going too fast? Yeah? Yeah, sure. So patient was treated, yes, so that was 1, and they went blind. So substitute 1 in here, and for t equals 1. And I hope I didn't put in a typo. It should imply that EB equals, and solve for EB, it should be 1. Can someone just double check that so that?
If t equals 1, the last term will always be 0.
Right.
And then the first t will be, what is the expression?
This is just a multiplication, right?
So that's t plus an error term?
No, multiplication. T times the error term, right? So then we've got, so this one is all 0, right? And then we've just got this, and t is 1, yeah, okay. So that's how I get that the error term in this case must have been 1, right? Now I can ask, what would have happened to the patient if they had been 0? Well, let's take these two, plug them in there. Then the answer would have been that they wouldn't have gone blind, okay? So now the patient might want to sue, right? Want to say, hey, you shouldn't have treated me, right? So the question is, did the doctor make an error in treating this patient?
Couldn't the patient also ask, or like, do we know that whatever the treatment is actually does cause blindness?
Yeah. Good, exactly. It's a different question, right? So in general, it's not, it's does this treatment actually cause blindness or not? Well, what quantities answer that question? It's these quantities here. It's the average treatment effect. What is the probability of B equals 0 given that I intervene to treat versus what is the probability of B equals 0 given that I don't treat? Yes? Well, how do I compute these? These are given just by this formula here. I'm not doing anything interesting there. That's you would figure that out too. I don't know if you can work it out that fast. I don't know. Can anyone see what the answer is? Should the doctor have treated? Let me give you the answer, and then let's try and recover it. The doctor, the probability of not going blind, given that given that you don't treat, is 0.99. The probability of not going blind, given that you do treat, is probability of 0.01. Hang on, did I say that correctly? Probability of treatment and blind is, so you stay sighted is so probability that you stay sighted given that you treat is 0.01. I've flipped the numbers, haven't I? Probability of equal blind equals 0 given treatment.
Unless
Hang on, did I flip the numbers? Blind is 0. I flipped the numbers here, I'm sorry. This should be the other way around. So I'm sorry, this is an error. Because what actually is the case, if I treat, then the probability that I go blind, which is b equals 0, b equals 1, is low. So this is, I should either have a 1 here or I should have 0.99 here. And the probability, if I don't treat, that you go blind, which is b equals 1, is high.
But you only can do that when you know that a possible outcome of the treatment is going blind. If something else would come up,
Yes. Okay. But so I've specified in this case, so this is why this was the answer before. It's a contrived example because I've set up the entire thing before. I've said this is everything that's going to happen. If that's everything that's going to happen, then then I can work out, in this case, to say, on average, what do I expect this treatment to be? And on average, this treatment helps to prevent blindness. But it just turns out that in this specific case, the patient was extremely unlucky, and for that patient, we should have not treated. Yes? No? Maybe? Not confident. Okay, so I don't have much more. So I'm going to stop after this slide for our break. So the reason why I think we need this sort of technical setup for causality is because it brings three quite different concepts together in one toolbox. One is that you can actually predict. That's what machine learning does as well. It is very good at doing all sorts of predictions, never mind what the causal structure is underneath, right? So if I can predict y from x because x causes y, or I can predict y from x because they're both correlated due to something else. But causality connects the prediction to the case where what happens if I intervene as well. So what happens in the system where when x causes y and I intervene versus what happens in a system where x is confounded by something and I intervene. Because here, if I want to have a policy recommendation to do something that changes x in order to change something about y, but my situation causally is like this, then I wouldn't have any sort of effect. And I want to be able to answer counterfactual questions like what would have happened if something had been different. And these three things come apart. Like the blind patient is an example that shows that, is that we can predict what would happen. We can predict what happens under intervention, but that's still a separate question, what would have happened counterfactually, right, of what would have happened to them. So let's take a break here, and I'm going to check on where my error is in that slide. And we'll be back in, what, half an hour or something like that? Is that the...
15 minutes.
Yeah.
we usually have like 10 or 15 minutes.
Yeah, so let's come back at 11. Okay, thank you. Sorry about the couple of places where I ran myself into a hole.